Welcome back to our section on equilibrium. We're going to do a little bit of review, just remembering what equilibrium is. We're going to look at something that's exciting because it's a mathematical expression that will help us to get a clearer and more concise picture of equilibrium. We're going to look at the equilibrium expression. And therefore also the equilibrium constant. And so we'll be doing some math and some calculating. We are also going to look, remember we talked about homogeneous or homogeneous reactions and heterogeneous reactions. We're going to look at what that entails for us in the state of equilibrium and how we do calculations with different kinds of equilibria reactions. So let's just start by reviewing a little bit. These are concepts we've already talked about, but we're just looking at them in another way. If you look at this system, we're looking at some reactants here and some products. And if we think about this system as each blue circle being 1 mole, here we start with all reactants. Put all our moles in one bucket. And this is what we look like initially. We may let a little time go by and then check back in, and we see this happening. It's almost all products. There's only 1 mole of reactant there. That would be our next phase. And then maybe we check back again and we start seeing this happening. We have a little heavier on the reactant side, only 3 moles of product. And here we finally achieve a dynamic equilibrium. Remember, dynamic equilibrium is where the concentrations of the reactants and products are remaining constant. They're remaining the same. They're not changing. It is also the point at which the forward rate is equal to the reverse rate. So both of those things are happening in our dynamic equilibrium. It does not mean that we have equal concentrations of products and reactants. That's a really important point I want to make sure everybody understands. This is dynamic equilibrium, but the concentrations of the products and reactants are not equal. The rate of the forward reaction is equal to the rate of the reverse reaction, and the concentrations of the reactants and products are not changing. So that's a really important distinction to make. Here are just some visual representations of what I just said. If we look first over here at this little illustration, if we have the reaction where it's leaning this way and we have the rate, the forward rate, this would be from reactants to products, the rate of the forward reaction being greater than the rate of the reverse reaction, that is not in equilibrium. Here we have the opposite. We have the reaction is going backward. Here we have the rate forward and the rate backward being equal, so we are in dynamic equilibrium. If you look at this graph, for those of you that are getting ready to take the ACTs, graphs are really important to be able to read quickly. What are we looking at? Rate versus time. What is this axis? Time. As time goes by, what am I analyzing in my graph? I'm analyzing the rate right here. And so I know I'm looking at time in seconds versus rate in meters per second. And I'm looking at the rate of the reverse reaction, and this would represent the rate of the forward reaction. My forward reaction is decreasing until I achieve some state of equilibrium. My reverse reaction is increasing until I achieve a state of equilibrium, and my state of equilibrium on this graph clearly shows my forward rate of reaction equals the reverse rate of reaction. Here we are looking at a graph that is talking about concentration. This is a really bad graph, by the way, because it doesn't have what? A title. It also doesn't tell me my units of either the time or the concentration. So don't ever make a graph like this. This is really bad. But I wanted to put it on here to show you just another way of looking at, as we increase in time, we can look at the different concentrations. Here's the concentrations, obviously, of the reactants. Here's the concentration of a product. And when these concentrations are all stabling out and not changing, they're no longer fluctuating, they're remaining constant, then I have achieved equilibrium. So now let's look at something called the law of chemical equilibrium. It's a big long word, or a big long idea. Sounds intimidating. It really isn't. Let's look at an equation, a chemical equation, okay? And we're going to call the capital A, capital B, capital C, capital D. Those are going to represent my species of atoms or molecules that I'm talking about. The coefficients, the little a, little b, little c, and little d, those are the coefficients in the chemical formula. When you balance your chemical equation, you place coefficients in front of each of the different species, right? Each of the elements or the molecules that are the reactants and the products, and that's what those are representing. Those are the lowercase letters are the coefficients. And for this system, we can write what is called an equilibrium expression right here. And this is how we write it. We call the equilibrium expression K, big K, capital K, is called an equilibrium constant. So our equilibrium constant, K, equals, brackets represent concentration of. So our equilibrium constant equals the concentration of C, it's over here on the right side, okay, to the power of its coefficient times the concentration of D to the power of its coefficient. And don't worry, we'll do some practice, so this won't be too intimidating. But you have the concentrations of the products taken to the power of their coefficient divided by the concentration of the reactants, each taken to their the power of their coefficient. So let's do a few practice problems. Remember, this equation is true only when the reaction is in equilibrium, okay? This is not true for the initial state or any state that is not in equilibrium. This is the equilibrium expression is true when our system is in equilibrium. Let's practice writing the equilibrium expression for this reaction. We know we're going to start our equilibrium expression talking about the equilibrium constant, K. K equals, now let's look at our products. We put products as the numerator. It's going to be the concentration of hydrofluoric acid, and we're going to take that to the second power. The coefficient is 2. That will be our numerator. And then remember, for the denominator, we're going to put concentrations of the reactants. So here are 2 reactants. We have hydrogen gas right there. Hydrogen gas, the coefficient for that is 1, right? There's just 1. Anything we take to the first power is itself, the identity property in math. So I'm not going to put any, I'm not going to put an exponent there. And fluorine is my other reactant. So I can write that, the concentration of that. And again, its coefficient is 1. So I don't need to put anything, I don't need to give it a power. That is my equilibrium expression right there. So let's talk about what is the significance of the equilibrium constant. It's actually really, really neat because it's constant. It means K is always K when that particular system at that particular temperature is at equilibrium. Let's look at an example. Let's take nitrogen gas plus hydrogen gas giving us ammonia, okay? When we look at this reaction, we're actually looking at, here's the balanced equation right here. Kind of highlight that for us. There's the equation. N2 plus 3 hydrogen, diatomic hydrogens give us 2 ammonia. molecules at 500 degrees C. Now, keep in mind, this is at a particular temperature. If we change the temperature, we're changing the energy that we're putting into that system, and our equilibrium constant will change. But at 500 degrees C, for this reaction, we can do several different experiments. We can start out initially with different concentrations of our reactants. Let's say for experiment 1, we start out with these concentrations of the nitrogen and the hydrogen. Let's say for reaction 2, we don't start out with any. We just start out with product. And for reaction 3, we do something even different yet. Okay, start out with some different concentrations. When this is done in the lab, these are the equilibrium concentrations. Notice that they vary between the experiments, the equilibrium concentrations. However, when we calculate K and we plug these values in to our equilibrium expression, the equilibrium constant is the same in each case, 0.0602. There are generally no units applied to K, just a FYI. It's important to know that there is one equilibrium constant for a system at a given temperature, because it all depends on the ratio of the different concentrations. And when that system reaches equilibrium, that K value will be the same. There is another term called an equilibrium position. The equilibrium position is basically the set of equilibrium concentrations. It would be these individual values are the equilibrium positions. And there's an infinite number of those because they depend on the initial concentrations of the system. When we put different initial concentrations in, we will get different equilibrium positions. But we will always have one equilibrium constant. So let's practice calculating an equilibrium constant. Here's a problem for us. Sulfur dioxide reacts with oxygen. Here I have sulfur dioxide and oxygen. They react in the atmosphere to form sulfur trioxide. Sulfur trioxide happens to combine with moisture to form sulfuric acid droplets, which is a component of acid rain. The following are results that were collected for 2 experiments involving this reaction at 600 degrees Celsius. The value of K should be the same for both experiments. So let's see if we can verify this by calculating the equilibrium constant observed for each experiment. First, what do? Whenever we're solving problems or doing calculations, we have to have a balanced chemical equation, and we do. They gave it to us, so we don't have to figure it out. How nice. So here's our equation. Now, we're going to solve for K. Let's write our equilibrium expression. K is going to equal our product squared, right, because we have a coefficient of 2, divided by, here's a reactant, the concentration of SO2 squared, it's an S, times the concentration of O2, oxygen. So now, for experiment 1, we can simply plug values in for that. We see right here the concentration. Now, something really important to note, they're giving us initial concentrations and equilibrium concentrations. Which ones are we going to use? The equilibrium concentration. This is an equilibrium constant. We wrote an equilibrium expression. These are values for the concentrations at equilibrium. So that's what we need to use, the equilibrium values. And when we do that, we see that at equilibrium, the sulfur trioxide is 3.50 molar, and that's going to be squared, divided by the concentration of sulfur dioxide is 1.50 molar squared, times our concentration of oxygen at equilibrium is 1.25 molar, and that is not squared. When I go ahead and punch all those numbers into my calculator, I get 4.36. I have 3 sig figs, matches the sig figs there. And remember that K values are unitless. So I'm going to check this against experiment 2. I'm going to look at the equilibrium values for experiment 2. And in that case, I'm going to get sulfur trioxide as, 0.2, boy, my pen's not working, 260 molar squared divided by my sulfur dioxide, 0.590 molar squared times the oxygen, just 0.045 molar. I'm running out of room, so I'm going to just go ahead and punch that into the calculator. I get 4.32. So here I have, go ahead and circle these, my K value for the first experiment and the equilibrium constant for the second experiment. So we can, due to rounding off an experimental error, they are slightly off, but they are nearly identical, and they are the same for all practical purposes because K is a constant. So we just verified that the equilibrium constant is indeed constant. Now you practice. Pause the video. Here's a little problem for you to do. See if you can calculate the value of K for this reaction at this particular temperature. Here's the answer for that problem. Hopefully you got that right, and we'll have more practice time in class as well, so you can work on more of these in class. Let's look at one final idea, and that is that there is a difference between homogeneous equilibria and heterogeneous equilibria. And you're going to like this because it's much more simple for heterogeneous equilibria. In fact, it's incredibly simple. First of all, let's look at what we've been looking at so far. If you haven't noticed, we've been looking at homogeneous or homogeneous equilibria. They've all been in the same state. If we take a look at something that is not, like this heterogeneous equilibria, this has more than one state involved. We have solid, solid, gas. I would like you, first of all, just to think about the fact that pure solids and pure liquids cannot change their concentrations. They are pure solids and pure liquids. So they do not have fluctuating concentrations. Their concentrations are constant. Therefore, for this reaction, this is not the equilibrium expression or the equilibrium constant, because these values, the value for calcium oxide and calcium carbonate, are themselves constant. So how do we figure this out? What are we going to do about this? It's so nice and easy. Look at this. Because the values for the solids, or if they were liquids, it would be the values for liquids as well, are constant, I am simply going to put, instead of the concentration of those, I'm going to label them in my expression as being constant. I'm going to call them a C constant instead of a K constant. C1 for this one and C2 for this one. If that is true, then I can simply say, I can do a little algebra here, right? I can multiply both sides by constant 2. That gets rid of this. I can divide both sides by constant 1. Gets rid of that. And I have my equilibrium constant times C2 over C1 constants equals the concentration of CO2. Well, if I take a constant times a constant divided by a constant, do I still have a constant? Yes, I do. So I can simply write the equilibrium constant as K equals the concentration of CO2. It is the only one in gas form. This is important because you need to remember it applies to gases and it applies to solutions. Okay, so those vary. Pure solids and pure liquids do not vary, they are constant. But solutions and gases have variable concentrations. Their concentrations can vary, and therefore they will be what is represented in our equilibrium expression. So you try it. Here's a practice problem for you. Solid phosphorus pentachloride is decomposed to liquid phosphorus trichloride and chlorine gas. Write the expression for K. What are you going to do first? Please write the balanced chemical equation first. Here's the answer to your problem right there. Very nice and simple. So probably the most difficult part of that was simply writing the balanced chemical equation. So please complete the worksheet for this section. Do some practice. Here's an advanced idea. Instead of what we've talked about is equilibrium, the equilibrium constant as it relates to concentration. Sometimes you'll see that written as Kc. It has to do with concentration. Did you know that we can also calculate it in relation to pressure? How do you do that? That is for advanced proficiency. If you'd like to look into that, you'll have to research how to calculate mole fractions and partial pressures. And if you're up for the challenge, go for it. If you can think of another great question to ask or some more advanced proficiency ideas, I'm open to whatever questions you have or whatever you'd like to research. So we'll see you in class.